Hello, thanks everybody for being here. And yes, today I would like to tell you about our fluid dynamic approach in order to study the dynamics of heavy quarks in the quark-gluon plasma produced in a heavy ion collision. Yes, so first I will go through some introduction and the theoretical setup that we use. Then I will focus a bit on the numerical methods that we implemented to solve the equation of motion. And then I will show you some phenomenological results, and then I will talk about our latest developments. So let's start. So for probably many of you are familiar with this, but heavy quarks, so charm and beauty quarks, are a wonderful tool to study the properties of the quark-gluon plasma produced in heavy ion collision. In fact, here you see depicted the sketch of a heavy ion collision, and the heavy quark, like charm and beauty, are produced even before the quark-gluon plasma phase is formed. And therefore, they have the advantage that they go through all the stages of the expanding fireball, and they interact with the light flavors of the medium, mostly elastically in the low transverse momentum regime in which I'm interested in. And then eventually they undergo hadronization, such as all the other particles. So we will measure charm quarks inside hadrons, such as the D0 mesons, which, for example, contain a charm quark. And oi, oi. Whoa, whoa, whoa. No spoilers. Okay. Okay, wait a second. Sometimes this interval option activates and then it goes automatically very fast. But, okay, no, should be fine. Yes, so heavy quarks initially are produced out of local chemical and kinetic equilibrium. However, in the low transverse momentum region, they provide us a window to study equilibration processes. And in fact, recent measurements of elliptic flow of J psi and D mesons really showed that heavy quark do display a positive elliptic flow, and it's of the same order of magnitude roughly as the one of the light flavor hadrons. And this really raised the questions of whether the charm quarks in particularly join the collective motion of the surrounding medium, and so whether they actually reach local kinetic equilibrium within the lifetime of the quark-gluon plasma, and whether they can be considered as a part of the medium itself, so we can treat them collectively with the surrounding medium. And in this work, we adopt this strategy. And so we want to address the heavy quark dynamics with fluid dynamics, such as the rest of the surrounding QGP. Yes, so in order to do fluid dynamics for heavy quarks, first of all, we need the standard equations for fluid dynamics for the surrounding medium. So we have energy momentum conservation. We have an equation of states that tells us the pressure in relation to temperature. We work here at LHC conditions, so no chemical potential, baryochemical potential. Plus the additional equation of motion for the dissipative charges. And then we need some additional equation for the heavy quark sector. So in particular, we consider a conserved charge that is the total number of heavy quark anti-quark pairs in the medium. And this is because the heavy quarks are too heavy to be produced thermally within the lifetime of the QGP at these energies, but at the same time, the annihilation processes that would annihilate a heavy quark anti-quark pair are also negligible within the lifetime of the system. Therefore, this charge is effectively conserved. And we can write a current associated to this charge that is conserved. And the way we write this current is this. So we decompose it in a part that is parallel to the fluid for velocity u mu via the heavy quark density. And then we have what we call the heavy quark diffusion current that is orthogonal to the fluid for velocity. Then we need to specify furthermore an equation of state for the charm sector. So we need to specify how the density of heavy quarks is related to the temperature and to alpha that we define as the heavy quark chemical potential divided by the temperature of the medium. And for this, we use the hadron resonance gas of all charm states. And finally, in order to describe the dynamics of the heavy quark diffusion current in a Israel-Stewart formalism, we need to specify an equation for the diffusion current that is displayed here. So what you see is that basically the evolution of the diffusion current is mainly driven by gradients of the heavy quark chemical potential divided by the temperature, so this alpha that I was mentioning before. And then the evolution of the current is tuned by two transport coefficients. One is the heavy quark spatial diffusion coefficient, ds, and this is something that we are also phenomenologically interested in because it's really a property of the of QCD. And the heavy quark relaxation time, tau n, which tells us basically after which time scale the heavy quarks approach a fully fluid dynamic regime. And yes? Yes, this is just for simplicity, but yes, it is, but so it is, but at the same time, we basically we don't consider the feedback from the charm sector on the bulk sector. So in the equation of state, indeed, we don't consider the dependence on alpha because we assume anyway that they are produced in a low amount. We also calculated at some point the actual contribution to the energy density, and this is very small in comparison to the surrounding. So actively the fluid fields of the bulk, so temperature and so on, are not influenced by the heavy quark dynamics, and only the heavy quark is influenced by the surrounding medium. Yes. It is for the charm sector. And so this is a long story. So in principle, yes, at very high temperatures, we would expect eventually maybe the heavy quarks to approach a free limit. So we would have the equation of the free charm, and at low temperatures, instead, we can rely on this hadron gas approximation. It's very important that when we hadronize, we are in the regime of a hadron resonance gas. Is the average of the density of charm plus anti-charm. No, I mean we don't consider the charm as a free charm. Okay, so the point is that there is no at the moment a first principle equation of state that tells us all the way through how the charm density behaves, and so we do this because at the moment we cannot do better. Yes, because the problem is, so it stemmed for maybe the phenomenological nature of the problem, but if you are at freeze out and you implement the free charm equation of state, you will not get the right distribution of hadrons at freeze out, so across the different charm hadron species. And so what we understood is that it's important that when we approach the freeze out, this is the equation of state, and this should be it. Yeah. Yes, one other option could be, we're thinking about it, to do some sort of interpolation between the equation of state, so assuming at high temperature the free charm and at low temperature the charming hadrons. Yeah. yeah, then maybe you have to wonder whether this works. We can discuss maybe later. But, yeah, yeah, mm, yeah, mhm, yeah. Okay. Yeah, we can come back to this later, maybe. Yes, so first I want to tell you about how we derived an expression for these transport coefficients that appear in the diffusion equation. So what we use is what's called the method of moments that is widely used, usually from a full Boltzmann equation. One integrates moments of the distribution function to get equations for the moments that are then the hydrodynamic quantities. And in this case, we exploit the fact that the heavy quarks are heavy to use the Fokker-Planck approximation of the Boltzmann equation. And this is an approximation that is valid in the limit in which the momentum transfer between the heavy quark and the other constituents is small. And then the collision integral, that is the right-hand side of this equation, can be written in this way, so like a Taylor expansion, and all the interaction is encoded in the drag coefficient A and the momentum diffusion coefficient D. And basically, if we integrate the zero momentum of this equation, we will get the conservation law for the heavy quark current. And if we integrate the first moment, then we get exactly the diffusion equation that we mentioned before. And we can identify the coefficients that we find from here with the transport coefficients that we defined in the fluid dynamic description. And therefore, we get an expression for the tau n and the kappa n, that is the spatial diffusion coefficient. And we express this in terms of this ds, so the heavy quark spatial diffusion coefficient, that is again the phenomenological property that we are interested in. And just one caveat is that in order to get exactly this expression, you have to neglect the momentum dependence of the drag and the momentum diffusion coefficient. So it's integrated out either way, but in this case, it was assumed to be constant so that it could go out of the integral. Otherwise, you should assume some momentum dependence. Yeah. Yes. So indeed, when we started this work, it was before we were even considering having more species. And so at the beginning, we did the treatment just considering one charm species. But indeed, also with Eduardo and Rossana, who is in the audience, we are now also working on really systematically implementing these multiple species. And in the end, I will show something about this that leads indeed to a modification of the definition of the transport coefficients and then basically each hadron will get a different F and delta F contribution to its final distribution. So yes, this assume that it's just for one charm species, but then we have ways to generalize this. Yeah. Yes, so then one first consideration that we did was to basically compare the relaxation time that we get in this fluid dynamic approach with what's defined in the standard way in the Fokker-Planck approach as the typical kinetic relaxation time of the heavy quarks, which is just given by the inverse of the drag coefficient, basically, time the temperature. And what we can see is that in the non-relativistic limit, the two descriptions converge, but when we go to lower m over t values in our approach, so in the hydrodynamic approach, we don't have this linear scaling with the mass over temperature, so we always have a finite relaxation time, even for quarks with zero mass, and this is also important for the causal evolution of the Israel-Stewart equations. Yes, and then one further point I want to make is that now we can define a relaxation time for the heavy quarks, and what we said is that the relaxation time in Israel-Stewart basically gives us a typical time scale after which the heavy quarks will fall under a fluid dynamic description. And what we can do now is to compare the relaxation time that we obtain for the heavy quark with the other typical time scale evolution that we have once we have a QGP that is actually expanding. And if we consider, for example, a Bjorkin flow, we can calculate the typical expansion time of the fluid from the inverse expansion rate analytically. And if we plot this expansion time as a function of the longitudinal proper time in Bjorkin flow, it's just a straight line because it's just given by the longitudinal proper time indeed. And then basically, we can compare the relaxation time of the heavy quark with this typical expansion time in Bjorkin flow. And if the relaxation time is much larger than the typical expansion time scale of the fluid, then fluid dynamics is not applicable because it means that the charm is not interacting strongly enough with the constituents. So it escapes from the medium evolution, basically. Whereas if it's below the expansion time, then a fluid dynamic description is applicable. And then what we did was to use basically the estimates from the heavy quark spatial diffusion coefficient given by the lattice QCD in yellow and from FITS to ALICE experimental data in blue. And we computed the relaxation time as a function of the evolution time. And what we see is that for a large portion of these values of the S, basically the heavy quarks spend most of the evolution time in the regime where fluid dynamics is actually applicable. So this is for the case of charm quark. So from this we said, okay, this seems to work, so we can try to apply really fluid dynamics in a simulation to see what comes out. Okay, and then one last point about the initial conditions for these fluid fields that we need to plug in into our simulations. So for the light sector, what we initialize is basically the temperature field for which we use for now a Trento model for the entropy density, and then we use the equation of state to obtain the temperature. And basically, we will assume that the temperature that goes into the equation of state of the charm is the same temperature of the surrounding medium because they are close to local kinetic equilibrium with it. Then we can use the expression for the density of hard scatterings of heavy quark anti-quark pairs. This is given by the first line. So basically what we need to know is the cross-section of heavy quark anti-quark pair production. We always work at mid-rapidity. So in particular, this cross-section in orange can be either given by FONLL, so perturbative calculation, or one could also take them from data in proton-proton. And then the further ingredient that we need is basically how the distribution of binary collision in the nuclear collision distributes as a function of the radius. And for this, we also use the Trento model. And then basically, we impose that the thermal hadron resonance gas of charm density that we use in the fluid description for the charm has to match the one that can be got through this procedure from perturbative QCD. And so this is what fixes the initial fugacity alpha unambiguously, and then we evolve it with the equation of motion. Okay. Now I will, for a second, pause and go through the numerical methods that we implemented in order to study this. Yes, go through time. Okay, so the equations that we have to solve for the heavy quark sector, as I mentioned, are a conservation law for the heavy quark current and an equation of motion for the dissipative current. So by construction, we cannot have a conservative form for this equation that express the whole of it as a gradient of some quantity. So one has to be careful when deciding how to solve it. And in particular, sometimes the method that it's used is to basically split the equilibrium contribution. So here would be the one from the equilibrium density from the dissipative corrections. But we didn't want to do this because in principle, these dissipative corrections can be hard. And so we want to treat them all together as a system of partial differential equations. So basically, we collect the fluid fields in a vector. Here I only state the charm ones, but actually we do it with all the fluid fields. And then we can collect in a matrix all the coefficients that will be in front of the spatial derivative of these fields. And then we have a source. And yeah. Um, no, it's because basically we collected at the beginning all the matrices that are in front of the time derivative, spatial derivative, and so on, and then we do the inversion of the, or maybe I'm not answering the question. Yeah. Yes. Yes. Mm-hmm. And this here is, yeah. Yeah, this yeah, it's of the order of what we showed here. So this is so the band is really the tau n as a function of the evolution time. This is Bjorkin flow, but more or less it's really small. So okay, depends of course on the ds that you use, but we stayed mostly in the lattice QCD regime, so to be safe. And so you can see that. It's really basically one Fermi over C at the beginning of the evolution, so it's quite small, yeah. Yeah, so the mass of the charm that we use is 1.5 GeV, and the initial temperature is of the order of 600 in the middle of the fireball, 600, yeah. Yeah, if I remember, yeah. Yeah, we fix the temperature as usual by basically fitting to the light flavor the normalization for the Trento profile. Hmm? Yeah. Um, yeah. So where is it, or? No, in this, so yes, I mean, in the, maybe, I mean, in the publication, you can find the covariant version of this. So there is also the contribution to the fluid velocity. So this was just an example in the fluid rest frame, just to show simply how the quantities relate, but in principle, actually, basically, the fluid velocity that we associate to the to the heavy quark is really the fluid velocity of the fluid with a small correction that is given by the diffusion current in the orthogonal direction. It is, yeah, yes. That's why also we can solve all together. Otherwise, we need many more equations. Okay. Yes, and so we get an equation of this sort, and the first thing one can do to do the discretization is just to say what's on the right-hand side, basically, so to take the central value for the difference of the fields to get the first-order derivative and write it like this. But this turns out to be unstable, so we cannot actually use it. And the reason is because the solution to this equation can be seen as a collection of waves that are interacting non-linearly with one another, and their velocity is linked to the eigenvalues of this matrix A that stays in front of the spatial derivatives. And so we will have positive and negative eigenvalues, and if we consider a one-dimensional case, this means that we will have basically waves propagating in the right direction and waves propagating in the left direction. And so when using this kind of discretization, it can be ambiguous because we can basically ask the derivative in a point in space where the wave has not yet arrived. And so the way to deal with this is called the upwinding method. And so basically this requires to separate the eigenvalues in a positive and a negative part of eigenvalues so that we always know in which direction basically the wave is propagating. And then we define the derivative differently. So in the case of a positive eigenvalue, we only take derivatives in the past of the wave, so in this green area. And in the opposite side, we do the opposite. So we take it in the future of the wave, basically. And in this way, we have now an unambiguous discretization in principle. And then one convenient way to express this positive and negative part of the matrix, it's also called the row matrix, is through the absolute value of A that can be defined through these relations. And in this way, we can now rewrite in terms of also this absolute value of the matrix, the new expression for the discretized evolution equation. And what we see is that now we have these two combinations basically of this, what we defined as negative and positive derivatives in this upwinding method. And we can work a bit with this. And the important thing is at the end, when we look at the final form for the discretized equation, we get a sort of a numerical viscosity, basically, that stabilizes the equation. So in this way, we kill basically the high frequency mode and our equations are stable. In principle, if these terms go to zero, we are solving the original equation. And this can be achieved if you see that this is proportional to delta x, that is basically the discretization of the grid, the lattice spacing. So when we go to very small distances, this goes to zero. And basically, this is the equation that we can use now to solve our system of equations. But one drawback is that at this point, in principle, one should know basically the full structure of this A matrix. So one should need all the eigenvectors and eigenvalues in order to do this. And this can be very expensive because, for example, in our system, in 1+1 dimension, only to solve all the equations for the heavy quark and for the bulk fields, we already have 7 equations, and we're just in 1+1 dimension. So the solution that was proposed by Castro and collaborators was to basically approximate the absolute value of this matrix with a function. So this function should be a good approximation of the absolute value in the range of eigenvalues in which you want to apply it. Should be easy to calculate because we don't want to trade the diagonalization of a big matrix with a very hard to compute function. It should be larger than 0 to be an absolute value. And for a stability condition, it also should be larger than the absolute value in the range of eigenvalues that we are considering. And the simplest solution to do this is to consider this approximation. So you see that you have a larger deviation at 0 eigenvalues, and then when you go to 1, you have instead a good approximation. Now we can check whether this is a good choice, basically. And so what we did at the beginning was to basically validate our code with semi-analytical solution, so with Gubser flow. So on the left, you see at different times how the temperature evolves in the two setups, and also the chemical potential of the heavy quark to temperature ratio alpha. And from here, you cannot really tell the difference, basically. And then we can also look at dissipative quantities. So for example, here is a component, the phi component of the shear stress tensor divided by the entropy density. And so also here at naked eye, you cannot really tell the difference between these two. Actually, what we saw is that the numerical viscosity actually modifies the dissipation of the system. So when going further in the time direction, you will see more and more deviations, especially where the viscous corrections are very large. And on the right plot, we evaluated basically the absolute difference between the numerical and analytical solution. You can see, as expected, that the more points you have in your grid, so the smaller is the lattice spacing, the better the two solutions agree. So this is good because it means that we can control basically our approximation of the real solution. And one thing that we can notice is because of this numerical dissipation, when you will have large dissipative correction, there is also where you have the largest deviation from the real solution. And this is also seen basically when we compute the relative error with respect to the real solution. And then what we're interested in eventually is to conserve this total number of heavy quark anti-quark pairs in the medium. So we can go back to our conservation law that in our 1+1 dimension is written like this. So it will be given by this radial integral of the time component of the heavy quark current. And we can plot it as a function of time. And here, the different colors are for a different number of points in the grid. In the left case, with spatial diffusion coefficient equal to 0, and in the right-hand side with 0.4. And what you see is that, of course, the algorithm cannot be perfect. So we expect that it's still going down a bit. So it's not perfectly conserving the number of charm quarks, but we can improve the conservation with the number of points, for example. Sorry? Yeah. Yes. So that's why we expect it. No. Yeah. You mean to split the evolution bulk and the charm? Mm. Yeah, we can. I mean, we can consider. I think, yeah. Yeah, I think this is a valid point. We can consider this. Yes. And then basically, so first I show you like a first approximation of this algorithm, and then we already wondered whether we can do better in this direction, so to be more conserving with respect to the heavy quarks. And so one option is to basically use a more sophisticated way of approximating the absolute value of the function. And an example is with Chebyshev polynomials. So here the blue is, as usual, the absolute value. The orange is the one that we used before. And now, basically, a fourth order Chebyshev polynomial would give you the green line. So it's closer in value to the one of the absolute value. So one expects a higher accuracy. As I said before, for stability, one should be careful that the value of the function is always larger than the absolute value. And here, this is not the case. So the authors originally proposed to add like a small finite value to it, but then they found that when actually applied in numerical computation, there was not really a difference. And so for now, we also didn't include it. And again, here one has kind of a way to control the order of this accuracy, because the the error with respect to the real solution decreases with the inverse of the order of the polynomials, basically. And then here we again went to look at the conservation law for charm. So again, the number of charm as a function of time. And here, yeah, the quality of the plot is not amazing, but if you see on the left plot, the dashed lines are the ones computed with the previous normal upwinding algorithm, and the solid lines are the one with the Chebyshev. And so one can see that Chebyshev systematically, for the same number of discretization points, manages to conserve better the number of charms. So this should be a better choice with respect to the previous one. And then again, we looked at basically how the number of charm is conserved when varying the spatial diffusion coefficient. Yes. So from the left-hand side, what we learn is just that if I compare curve by curve for the same number of points, Chebyshev versus the previous approximation, Chebyshev is always better. So from this, I learned to use Chebyshev. And then what we learn from both is that, okay, of course, if I diminish the lattice spacing, I get also a better conservation. From the right side, I learned that the algorithm conserves a bit differently when using different spatial diffusion values. For this, I'm open for discussions. Yeah. Yeah. We should, yeah. Principally, your grid should be larger, so nothing goes out. Yes. Mm-hmm. Yeah, I think here it was 30 Fermi over C, up to 10 Fermi over C. So in general, all the fields are fine. Only the fluid velocity can like be still big at very large, but okay. Not too much. Yeah, exactly. So. How big was your yeah, I guess the temperature drops at around like 7 Fermi. So it's the most no, this would be another discussion. No, this is the number of charm at fixed tau steps integrated over the radial region. So no, this is full Israel Stewart. Yeah, the fluid velocity initially is 0, and the temperature, we take the entropy density from Trento, and we normalize it by looking at the multiplicity of light hadrons. And then the diffusion current, you mean? Or the... yes, this we initialize to 0 at the beginning, so we don't assume a pre-phase for now. So 1 + 1, yeah. No. radial expansion. No. No. I mean, so yeah, I mean, it depends on the centrality you choose, where basically the profile goes to 0. In this case, I think was around 7, 8 Fermi. I mean, no, wait. This one is Rick, so here it's maybe a bit, tiny bit smaller, maybe 6 Fermi, but previous one was 7, 8. 30, 30, yeah. I mean, we are, yeah. Yes. There is one more thing that maybe we should be careful about. That is that basically we don't let the temperature exponentially going down, because it also numerically this is a problem. So we put some flat atmosphere, yeah, some temperature. Mm-hmm. Yeah. 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 Mhm. Ah, you mean, yeah, how much we are in the Navier-Stokes regime? Yeah. Mm-hmm. Yeah, exactly. Yeah, yes. Mm-hmm. Okay, good. Um, yes. Okay, so of course we can still do better because we're not satisfied, but this is only an outlook, so I will not explain you another method, but in principle one could also use rational polynomials like these highly rational polynomials that in principle get even closer to the absolute value. So this is one option to try in order to be better in the evolution phase of the charm. Basta. Okay. Now we can go to see some results of how we perform when compared to experimental measurements. And yes, so first I still wanted to show you. So this is again LHC central collision scenario. And here I show basically how the charm density evolves and how the radial component, that is the only one we have for the diffusion current, evolves in time. So in blue, non-diffusive, it's easy, the diffusion current is always 0. But of course, when you become diffusive, indeed, this pushes the density to be larger at larger radii. And this is because at the same time, we have the buildup of the diffusion current. So the diffusion current evolution follows the standard. So it starts from 0 in our case, it builds up, and then it goes again towards 0 at larger times. This is a bit related to what you were mentioning before, that is that in principle, we expect maybe a full hydrodynamic regime when the diffusion current is much smaller than the equilibrium density component. And this, of course, depends on the spatial diffusion coefficient that you're using. And maybe it's not true at all radii or at all times all the time. But at least the fluid dynamic equations are self-consistent, so the code doesn't explode, and so we can use this as a motivation to go further. Here is the results in comparison to integrated yields for charm hadrons at the LHC. So we use a Cooper-Frye prescription. So at this stage, to anticipate questions, basically we use a distribution function for each hadron that contains the mass of the hadron, the charm charge of the hadron. We don't include at freeze out at the moment out of equilibrium correction. So basically the component of the distribution function that would come from having a finite diffusion current, or in principle also from bulk and shear viscous pressure. This is something we're currently working on. If I have time, I have a few slides at the end. So with all these caveats, these are the results in blue. The ones without resonance decays fit down. In green, when we include all the resonance decays that are present in the PDG. So you see that in this case, we get very close to the data, especially for the meson sector. And one can see clear deviation for the lambda C baryon. Within our model, this could still be explained by the presence of resonance states that fit down to the lambda C, but have not yet been measured, or otherwise other approaches completely different that use a coalescence approach can also manage to describe this integrated yield. And then in principle, our approach as it is pretty general, so it's not hard to compute different species of particles. So in principle, we can propose our prediction for baryon states also that have not yet been measured. So the theoretical things here don't have error bars. There are, yes, I'm well, for example, the largest source of uncertainty that I show in a different case a bit later is already from the charm production cross-section. So already the number of charm is not fixed, and this basically linearly transposes in this final plot. So this is like the central value of this is the yield that we get from the central value of this estimate for the cross section, but in principle, this error should be propagated. Say it again, sorry. Yes. I agree. And I mean, this was yes, a first study also. We didn't really do fits, for example, so we didn't use best fit viscosity or spatial diffusion coefficient, but we just used basically central values of reasonable assumptions for all of this. And we're happy that basically out of the box, we already get a description that is close to the data. But then, of course, to be fully quantitative, one should be more careful and also work on this side of the analysis and error bars. In the next slide, you will see something that resembles an error bar. And this is, so this is a plot that shows the transverse momentum distributions for several hadrons as a function of PT. In this case, already with resonance decays. And basically, the error band that you see here is because we are not including right now the delta F correction, so the out of equilibrium part of the distribution function coming from diffusion, but we are varying the diffusion coefficient in a certain range. And so basically we are not accounting for the full number of charm quark in the medium artificially by doing this at freeze out. And so we have a bit of variation or large variation at the end. So actually working on the definition of this out of equilibrium correction at freeze out is something that we care about and we are currently working on. In disguise. Yeah, so the So, for example, the integrated yield that you see here is computed for spatial diffusion equal to 0, because this is the only case in which we are sure that all the charm that we put in, we get out when we decide not to include basically the diffusion current contribution to the distribution function, because it's not there at the s equals 0. So this is the only case in which for now I trust the integrated yields. In this case, instead, we vary the diffusion coefficient, but we still don't include this diffusion current component to the equilibrium function. And therefore, we get a variation in the integrated yields as well. And so, yeah, so basically now we are working on a systematic way how to include this in order to also shrinken these bands and see a bit better where we are in comparison with the experimental measurement. Yes, JPSI doesn't work, but yes, at a larger transverse momentum, one explanation can be that there is this fraction of primordial JPSI that basically doesn't dissolve in the medium, so it cannot be described by our thermal fluid dynamic approach, and this could be especially modifying the high transverse momentum region. Yeah, final thing on this side. This is a plot for the heavy core spatial diffusion coefficient as a function of temperature. And as you see, in general, it's not flat, apart from the IDS-CFT calculations. And so the results that I showed you before were if we basically take the value at the closer to the phase boundary and use it constant towards in the full evolution. Now I took a fit of the central point basically just to introduce a temperature dependence of the coefficient to see what happens. And on the right-hand side, you see the new results with this temperature dependence. And what you see is that basically it doesn't vary at all. So it seems that at least the transverse momentum spectra are not very sensitive to the temperature evolution of the spatial diffusion coefficient, apart from in the tails at larger PT. Okay, do I still have time? Otherwise, 5 minutes, okay. Then maybe I skip this part. So this is other phenomenological applications. I maybe prefer to focus 1 second on this last part. So as I mentioned multiple times, our heavy quark distribution function is associated to an equilibrium part that is the equilibrium density, and then out of equilibrium part delta F that will reflect into the heavy quark diffusion current. And for now, the current setup is that we put it at 0 at time 0, and we put it at 0 at freeze out because we didn't know how to deal with this. For what regard the freeze out, what Rossana is working on, and you can also see something in the slides, but I invite you to talk to her also. She's working basically on exactly implementing a different correction for each hadronic species. And so in this way, we will be able to take into account the diffusion correction at freeze out, as well as maybe also the corrections coming from the interaction with the bulk and the shear viscous correction at freeze out. And for what regards the time 0, we thought we were being sloppy, but actually we were being correct. So initially the diffusion current in our approach is really 0, because the cross-section PT differential only depends on PT. It doesn't have any radial dependency. And so by construction, the diffusion current is 0 at the beginning. However, we could remember that the heavy quarks are produced before the QGP starts. So in order to be a bit more realistic, we could consider basically a free streaming phase of the heavy quark before the starting time of the fireball evolution. And in this case, we would indeed obtain a non-zero component for the fluid, for the diffusion current at the beginning of the evolution. And so this is also another direction that I'm working on. So I will stop here then. And I thank you very much for your attention.
Sorry, I was had to go back. I missed the. How do you calculate the yield?
Yes, we use Cooper-Frye prescription plus resonance decays at freeze-out temperature of 156. Not chemical equilibrium with the rest of the medium because they will have a charm chemical potential that we obtain from the evolution. Yes, yes. Yes. Okay. I mean, it's basically this one actually. So in the Cooper-Frye, where okay, I mean, here it's. I can show you maybe later, but. Mu is the heavy quark per chemical potential, and we initialize it at the beginning of the evolution from perturbative QCD calculation. It's not, because because what they do is to have a fixed value for mu that is the same everywhere in space, and it's just used to reproduce the integrated yield. At the level of the yields, it's similar because it eventually doesn't make a difference because we just integrate out. But at the level of the spectra, this makes a difference because they cannot.
You mean that the difference is that now mu is a function of x?
Now mu is a dynamical variable that we initialize as with the other fluids, and we evolve dynamically until the end. Now, yes, it's a function of space-time. So on the freeze-out, it's not flat.
So this is just, okay, it's an amendment of this calculation. It's the same concept. So you have a number of quarks, which, okay, whatever they do in the plasma, and then eventually you recombine them into.
Yes, but it's not. Yeah. I mean, with respect to coalescence, we are on the statistical realization side. I agree. The only difference is that we don't need to basically fit the mu to the data or to the initial cross section, but we only use it as a definition from the initial time, and then we evolve it and we see what comes out. And actually, it turns out that the solution is very similar to the statistical organization model because.
Conceptually, the idea, the fact that one can fix it from the final data or not, but the idea is the same. The model is the same.
Yeah, it's a.
You recombine them statistically.
Yes. Mm-hmm.
Bit of a problem with your conservation problem. Initialize the density, the number of quark pairs, not the net one.
Mm-hmm.
So in principle, you're not conserving. What you evolve as a density, you're not conserving. What the total density, not the net density. So you should have something on the right-hand side that you can only divide. If you go back to the formula.
But we assume that the number is conserved because it is effectively conserved.
Both charm and anti-charm. The spirit of all this recombination of charm or stuff is create them, destroy them.
No, it's always that what you put at the beginning, you get at the end. This is also true for the statistical organization model. Charm plus anti-charm and. No. This is so the I is not anti or charm quark, but it is here because we use the density, the charm hadron resonance gas. So the I stands for different species. So the QI is if they have J psi as a 2 charm contribution and B0 as a 1 charm. It's just it's a positive number, but yeah.
They conserve both charm and anti-charm. Yeah. Yes, it's like it's the same thing as statistical collection. You completely neglect the reannihilation. Okay, very good.